If it's not your first day developing software with Swift, then I'm pretty sure you worked with protocols. They make your code more flexible and reusable, and I've already had a couple videos about that. What's important today is that Swift lets you use protocols almost anywhere, and sometimes you can't even say for sure whether a type you see is a class, protocol, or something else entirely. But what if I told you that this is only one of the possible ways you can use protocols in Swift? The other one has certain restrictions and requires more thought at design time, but it also offers huge performance benefits. So even if you stick to the familiar technique in most of your tasks, knowing about the alternative won't hurt. In this video, I'm continuing my mini-series on protocols. I'll compare their use as existential types and generic constraints. These two approaches differ in their syntax, use cases, and other aspects, so let's break them down one by one. And if you're interested in more content about software engineering, don't forget to subscribe to the Codebird. When people talk about using protocols in Swift, they typically refer to this. Here, the protocol name appears as if it were a concrete structure or class. And you can use protocol names in pretty much any place where you can use a concrete structure or class. For example, you can declare an instance property, pass the object in a function parameter, call its properties and methods, and so on. But in a way, all this is just a smokescreen, or at least a huge simplification. In a strict sense, protocols don't really exist at runtime. They're basically a build-time construct. The purpose of protocols in Swift is to enable compile-time type checking and define a contract that the compiler can enforce. If the conforming type violates this contract, your code won't build. But that's not to say protocols don't have implications at runtime. They absolutely do. However, these implications are not as straightforward as they might seem. But first, one formality. When a protocol is used like this, it's called an existential type. The name basically means that you can use the protocol as if it existed at runtime, even though it doesn't. That's possible through a hidden mechanism in Swift, and this mechanism impacts the code's performance. A few years ago, Swift even introduced the keyword any to make existential types more prominent. Again, because using them slows down the code. And here's how. To make the properties and methods of a protocol callable at runtime, behind the scenes Swift creates what's called the existential container. It is basically a black box that wraps around the implementing object. It exposes only the protocol requirements and forwards incoming calls to the implementation. The existential container acts like a proxy, similar to the site table that's created when you use weak references. And if you don't know what the site table is, I can dispatch you to this video. As you can imagine, proxying calls at runtime add some overhead. The question is there a faster way to do all this? There is. Actually, there are two ways for achieving that. The first one is using the concrete type directly. When you declare a protocol conformance on a type, the compiler forces you to implement its requirements. But if you then use the conforming type itself, the runtime doesn't need to use the protocol in any shape or form. It just knows that the properties and methods exist on the actual type. While there are valid cases for this approach, it's not what we typically want to achieve by using protocols. Usually we want polymorphism. In other words, we want our code to not know about the concrete type that implements protocol requirements. And we want the ability to swap the implementations as we please. So the other way of achieving better performance with protocols is by using them as generic constraints. Generics are a big topic in itself, but the general idea is that you declare placeholders for concrete types. When you then build the code, the compiler scans it for the types you've actually used throughout the codebase, and it can produce concrete versions of the symbols. It doesn't always work like that, but you get the general idea. And here's where protocols come into play. When you declare a generic type, you can restrict it by using generic constraints. Doing so instructs the compiler to make sure that every concrete data structure you use in place of the generic type declares a conformance to that protocol. If it doesn't, the code won't build. But if it does, the compiler will be able to emit concrete versions of all the calls. It will effectively bake the implementation into the codebase itself. The protocol is just no longer needed. The calls can be sent straight to the implementation, and again, there's no need for proxying. At least, this is the best possible outcome. As I mentioned, generics are a big concept that deserves a separate video, and maybe more than one. Some of generics aspects can be predicted with full certainty. In the next video on protocols, I'll delve deeper into the topic of their performance. But you should keep in mind that not every optimization that's possible in theory actually happens. A single generic parameter can have multiple constraints. For example, this method requires its parameters to conform to both identifiable and hashable, which is a common prerequisite for diffable data sources. In fact, generic constraints aren't even limited to protocols alone. For instance, these two methods accept subclasses of NSView, but also require them to implement the methods of the embeddable element protocol. Actually, generic constraints are even more powerful than that. But to achieve all their power, you need to use a slightly different version of the syntax. The where keyword is an alternative way to declare generic constraints. But unlike the angle brackets, where constraints let you be more specific. Perhaps you remember associated types in protocols. If you don't, here's my video from earlier this year. So, when you declare the generic types constraints using the where keyword, you can also constrain its associated types. In that earlier video, I demoed associated types using the concept of an object multiplier. Now suppose you're working on a class that uses that object multiplier, but only for strings. Using a where constraint, you can design this class in a type-safe manner by ensuring that the multiplier's associated type can only be a string. You won't be able to use any other implementation of the protocol. Perhaps from this illustration you can see the limitations of using protocols as generic constraints. You can try and drill this genericness throughout the entire type hierarchy, but at every level this list of generic parameters will only grow longer. What's the answer to this? Type erasure. As the name suggests, type erasure removes the information about object types, making them more universal. But by doing so, it also erases the benefits of generics, at least to some extent. The mechanism itself is quite simple. In the full implementation, you basically create an alternative hierarchy of classes. They erase types at every level. In a shorter version, you erase some types but leave others. For example, here I've removed generics that refer to the business logic component, but I kept the generic parameter for the type of data this component can process. What isn't that simple is deciding when to employ type erasure. On one hand, you don't want this tail of generics to pierce through all your classes, because it would make them tightly coupled, and that is something we try to avoid. But on the other, you do want to get the performance benefits of using generics. Basically, there's no universal rule. Using type erasure requires a careful balancing act between runtime efficiency and code maintainability. The rule of thumb comes down to the scope, usage requirements, and performance expectations. If generics penetrate the class hierarchy too deeply, or if you need to store multiple implementations in a single collection, or if performance isn't absolutely critical, then it may be a good idea to terminate that generic tail. But when your types are well contained, and especially when you want to squeeze every single memory bit and processor cycle from the device, then generics are the right tool to use, even despite their syntactic bulkiness. This has been another aspect of protocols in Swift. By now, you should have a pretty clear picture of why, when, and how you can use them. There is one more topic I want to explore, and it has to do with how protocols function behind the scenes. I already mentioned that protocols used as generic constraints work faster, and in the next video, I'll delve deeper into what this means exactly. Subscribe to the Codebird so you don't miss it. And if you found this episode helpful, give it a thumbs up. I'll see you in the next video. Until then, make your constraints fly.